Welcome back. We have already begun our study of multiple slit interference by looking at the particular case of the double slit, and we used the double slit interference pattern to come up with a formula for the location of the maxima and minima. That's the bright and dark fringes. And we'll see that as we add additional slits with the same slit separation, the location of those maxima and minima doesn't change. Some of the features of the pattern do change, and now that we've been introduced to phasors, we can use phasors to geometrically investigate how the interference pattern changes as we introduce additional slits. In this picture, we've got just 1, 2, 3 slits. So whether it's 3 slits, 4 slits, 5 slits, it doesn't matter for the purposes of this discussion. Here is an incident plane wave or laser beam incident upon 4 slits, and we've already talked about Huygens principle and how each of these slits can be thought of as the source of new circular wavefronts. So there really are circular wavefronts emanating from all 4 of these slits, and those waves have no inherent phase difference. They're all being, each of the slits is being illuminated by the same beam. So we've got 4 in-phase sources of waves, but we can use rays to examine the path length difference between the 4 waves as they all arrive at a particular field point P. So every point on this screen is being illuminated by all 4 waves simultaneously. And at some positions on the screen, those waves may be interfering constructively. At other points, they may be interfering destructively or somewhere in between. So we're going to investigate where on the screen we get constructive or destructive interference from these 4 waves. Just like before, we'll use the capital letter L for the distance between the slits and the screen. Lowercase d is the separation between the slits, and this is an important point. It's the same for all adjacent pairs of slits. So all of the slits are equally spaced. And in reality, capital L, in an actual lab setting, capital L is a much greater quantity than lowercase d. Capital L could be something like 2 meters, while lowercase d is almost always less than a millimeter. So this is a slightly more accurate picture. Even this is not to scale, because again, if this is 2 meters and the slit to slit separation is 1/10 of a millimeter, well, then you're talking about a ratio of something like, let's see, that would be 20,000. This distance of 2 meters would actually be 20,000 times as great as the separation between slits. Of course, if we drew it like that, there wouldn't be much to look at in this diagram. But you can see already that as we put the screen much farther away from these slits, compared to the slit separation, then these rays look more nearly parallel. And they're all making basically the same angle theta with the forward direction. So the forward direction, when I refer to the forward direction, that's the direction from the center of the slit pattern to the screen. If we zoom in, these rays look more nearly parallel. Again, they're not totally parallel, because if they were, they would never meet. And the whole idea is that they do meet at the field point P, but it's so far away, we can just pretend they're parallel. And now we can look at the path length difference between 2 adjacent waves. So we'll start with the top 2 slits. You see that this second wave has to travel just a little bit further than the wave from the top slit. And the geometry is identical to what we looked at in a previous presentation. If theta is the angle between the direction of the rays and the forward direction, that angle must be the same as the angle in this little skinny triangle. And again, to see that, as you let theta go to 0, in other words, as you bring these rays back down horizontally, you see that this angle would close up. So this angle and this angle vary together. They've got to be the same angle. So we could zoom in on this little right triangle here. I say right triangle because I've drawn a line perpendicular to the bottom ray here. We're interested in this side here that's opposite theta. The segment that I've highlighted in purple, is it purple or is it violet? I'm really not sure. That's the side opposite theta. So we take the hypotenuse, which would be the slit separation, we multiply by the sine of theta, and that gives us the extra little distance that the bottom wave has to travel. We've seen this already. So these two waves may or may not arrive in phase. They may be interfering constructively at the screen or destructively or something in the middle. It really depends on what theta is, because when you plug in different values of theta, D is not changing. Different values of theta produce different path length differences. And how the path length difference compares to a wavelength is what determines whether these waves arrive in phase or not. Remember, if the path length difference between the two waves is a wavelength or two wavelengths or three wavelengths, etc., then they're still in phase, so to speak. The crests arrive with the crests from the two respective waves, and the valleys line up with the valleys. You could make the same argument for the next pair. So if I call this wave 1, wave 2, wave 3, now look at how wave 2 and wave 3 interfere when they arrive at the screen. Wave 3 has to travel a little bit farther than wave 2. And the path length difference here is the same as it was up here, because it's the same triangle, right? The same skinny little triangle that we're using to determine the path length difference, delta R. So you really only have to do that once. Once you've determined the path length difference for the top two adjacent slits, it's the same path length difference for the next pair of adjacent slits. And that means that the phase difference between each pair of adjacent slits is the same. So to be clear, when we talk about two waves arriving in phase, we really mean that the phase difference is 0 degrees or 360 degrees or whatever, 720 degrees. If they arrive out of phase, we say that the phase difference is 180 degrees, or what would be after that? 360 plus 180. I'll let you do that. Now, it doesn't have to be exactly a destructive interference or constructive interference. It could have a phase difference of something like 5 degrees. Whatever the phase difference is between these two waves, it's the same as the phase difference between these two waves. So you only have to calculate that phase difference once. Once you've picked a particular angle out to the screen, you only have to make the calculation of the phase difference once. And that's because the slits are all equally spaced. You'll recall that the total phase difference between the arriving waves has a contribution from the path length difference and a possible inherent phase difference. Again, all the slits are being illuminated by the same laser beam. We're assuming that the beam is wide enough to illuminate all slits simultaneously, so we don't have to worry about the inherent phase difference. And that means after plugging in this expression d sine theta, which we got from the previous picture, you plug that in here, and you end up with this expression for the total phase difference. So there are arguably three quantities that determine whether the arriving waves for two adjacent slits are in phase, out of phase, or something in between. It depends on the separation between the slits. It depends on the wavelength of light you're using. So if those waves are arriving in phase for green laser light, they probably won't be arriving in phase for red laser light. And of course, it also depends on the direction you're looking. Where on the screen are you looking? What's going on here? Here's a phasor diagram where we've got one phasor each for the four slits. E1, this phasor right here, represents mathematically the wave arriving at this arbitrary point on the screen called P. Remember that this phasor is rotating in time with angular velocity omega, and that omega is the same omega that shows up in kx minus omega t. It's the frequency of oscillation of the wave. The length of the phasor E1 represents the field amplitude, the amplitude of the electric field from slit 1. The red projection onto the horizontal axis is the instantaneous value of the field in time. So as phasor E1 is winding around in circles, the horizontal projection will oscillate sinusoidally. It will grow to its maximum positive value, then shrink back down to 0, and then decrease to its lowest negative value, and just keep repeating that. And all of these phasors are doing that together. In fact, they're all rotating around the origin with the same angular velocity because each of these waves comes from a slit illuminated by the same laser. So you have to imagine this entire chain of phasors rotating around the origin at some angular velocity determined by the frequency of the wave. And the important, or maybe for our purposes right now, the most important thing about this phasor diagram is this phase difference here. So if you're going in the direction of phasor E1, you have to bend counterclockwise a little bit to represent the phase shift as you go from wave 1 to wave 2. The fact that these phasors are not parallel represents the phase difference between the two waves arriving at that point. The wave from slit 2 had to travel a little bit farther, and as a result, it picked up a little phase shift with respect to wave 1. Same thing for the wave arriving from slit 3. The wave arriving from slit 3 had to travel a little bit farther than the wave coming from slit 2. And so it's got a phase shift with respect to wave 2. But in each instance, the phase shift is the same. You see that the amount by which each next phasor is rotated counterclockwise is the same as you go from one phasor to the next. Why is that? If I go back, it's because the separation between adjacent slits is the same for every pair of adjacent slits. And you can also see that the horizontal projection is different for each of these phasors. This one has the greatest horizontal projection at this particular moment in time. This one's got the least. So that tells you that the instantaneous values of the fields are different at different times. They're not all in phase. If they were all in phase, then their horizontal projections at any moment in time would be equal. And just like for the case of two phasors, the double slit, because we've looked at that already, or did we? Did we look at phasors for a double slit or just one slit? Two slits. Now we've got four phasors. You put them all tip to tail, as I've done, and you draw the overall vector that goes from the tip of the first one, no, the tail of the first one to the tip of the last one. That is the net phasor. Now, I'm trying to avoid calling them vectors, even though they behave exactly like vectors as far as addition goes. I don't want to call them vectors because, again, this arrow that I've drawn here, the direction doesn't tell you anything about where the E field points in space, the total E field. That's not the significance of this direction. Remember, the whole thing's rotating anyway. So this green vector is rotating in circles at the same angular velocity as each individual phasor. It's the length of the phasor that we're interested in. The length of that total phasor represents the amplitude. I'm getting it right this time. It's the amplitude of the total electric field at the field point P. And depending on where you look on the screen, the way these phasors add up may be different. And that means the length of the total phasor will come out different. And that means that the strength of the overall field, or the amplitude of the total field, will come out differently. So the phase relationships between all of these electric fields arriving at the point determine the amplitude of the total field. And that's what tells you whether you're looking at constructive interference, max constructive, or max destructive, or something in between. It's the purple projection here that gives us the instantaneous value of the total phasor. Now, I made a goof in the previous presentation. I started out with these phasors using green for the total phasor and purple or violet for its horizontal projection. And then I ended up using purple for the total phasor. Oops, hopefully that didn't confuse you. I'll be consistent here and stick with green for the total phasor. Purple is its instantaneous value. Now, you have to imagine this green phasor rotating around and around, and you see that the greatest length ever attained by the purple projection will be the green length, right? Look at this overall phase. Look at the angle that E total makes with the horizontal axis. When that angle goes to zero, like as you imagine this rotating around, when the green arrow is parallel to the horizontal axis, then its purple projection will be equal in magnitude to the green arrow. That's the whole point, right? That after you've added these phasors up graphically, you now know what's the amplitude. When I say the greatest absolute value or the greatest magnitude taken on by the instantaneous field, I'm really talking about the length of this total phasor. So the length of the total phasor, once again, is the amplitude of the total field. Okay, so can we use this geometric construction, if you want to call it that, to calculate the phase difference delta phi? This is the phase difference between two adjacent slits. Which values of that phase difference will result in maximum constructive interference? That's a pretty easy question to answer. Pretty obvious, right? When they all point in the same direction, then when you add them, you get the longest possible total phasor. Pretty simple, right? So if they point in the same direction, that would be a phase shift of 0 radians between each successive or each pair of adjacent phasors. I should say adjacent slits, and the phasors associated with the waves from those two slits. Now, 2 pi would work just as well as 0 pi. Let's start with this first phasor. If we took the direction of that first phasor and then rotated by 360 degrees, we would be right back where we started. So the second phasor, if it had a phase difference of 360 degrees with respect to the first one, would still be pointing in the same direction. So a phase difference of 2 pi works just as well as a phase difference of 0. Same thing with 4 pi, 6 pi, etc. We already knew this, right? The condition for maximum constructive interference for two slits was that the total phase difference is 0, 2 pi, 4 pi, etc. Well, now we're asserting that the same condition holds true for 4 slits. And if you think about it, there's nothing about this argument that depends on the number 4. It could be 5 slits, any number of slits, as long as the separation between the slits is the same. And we've motivated this condition graphically here. It's really easy to see why this holds true when you use the phasors. So let's look at the slightly more difficult question. Which values of delta phi, that's the phase difference between the waves from adjacent slits, will produce maximum destructive interference? And I put perfect here in parentheses because, remember, we're not really worried about how the amplitude of each individual field or wave decreases with distance from the slits. In reality, if you go 1,000,000 miles away from the slits, there's not going to be any light intensity coming from any of the slits because you're too far away. It's not going to be 1 over r squared because we're talking about a laser beam, which is different from an isotropic radiator. But the extra distance that each of these waves travels compared to the one above it is so small, we're not worried about any decrease in the field amplitude. So from here on out in the presentation, we just assume that each of these phasors from the individual slits has the same length, okay? Saying that the phasors all have the same length is equivalent to saying that the amplitude of the individual wave from each slit is the same. Okay, so check this out. I will just show you graphically how a particular phase difference between the waves from adjacent slits can produce perfect destructive interference. Let's suppose that the wave arriving from the top slit at this moment in time has an overall phase of 0, which means it just points horizontally, and that the wave from the second slit is phase shifted by 90 degrees. So whatever that path length difference is, d sine theta, between the top two slits, it's such that the waves arriving at point P from those two slits are out of phase by 90 degrees. Well, we know that the phase difference between adjacent slits is the same for every pair because the slit spacing is equal for all pairs. And that means that the next phasor will be shifted 90 degrees from this one. So pay attention to the direction. We were going in this direction for phasor 1. We rotated it counterclockwise by 90 degrees to represent the second phasor. And that means we'll have to do the same thing again. Go in the direction of the second phasor and rotate counterclockwise by 90 degrees. And we find that the third phasor points in this direction. That's 3 phasors. We have 1 left to represent the total field from all 4 slits. Same thing, go in the direction of that phasor, phasor 3, rotate counterclockwise. And now we find that when we add the 4 phasors, the total phasor is the 0 phasor. I can't even draw it, right? That would be the phasor that goes from the tail of phasor 1 to the tip of phasor 4. Well, those 2 points are the same, so I can't even draw the phasor. That means that the amplitude of the total field is 0. Remember that the length of the total phasor gives you the amplitude of the total or net field, whatever you want to call it. So these 4 waves are arriving in such a way that, or the phase difference between them is such that the total amplitude of the field is 0. That means we get perfect destructive interference. You're very familiar with the notion of perfect destructive interference, but earlier in the semester, you were always imagining interference between 2 sources. Now we're looking at 4 sources and finding that altogether, you get perfect destructive interference. If you just look at the interference between 2 individually, you don't get perfect destructive interference. In fact, forget about this phasor and this phasor. If the only 2 waves arriving, from the top 2 slits were this one and this one, then the total phasor would be represented by the hypotenuse here, whose amplitude is clearly not 0. So you would not get total destructive interference from 2 slits alone. But with all 4, having the phase shift of 90 degrees between each pair, you do get total destructive interference. Okay, so I suppose it's worth noting that for 4 slits, a phase difference of 90 results in 0 total field or net field. And again, once you know the phase difference, because we've just determined that 90 degrees will produce perfect destructive interference, if you happen to know the wavelength and you happen to know the slit separation, you could then calculate the angle at which that happens. In the following slides, we're going to determine all the phase differences that produce max destructive interference or perfect destructive interference. And so theoretically, we could find all the angles at which you would find a dark fringe. But we're not going to do that. We did it for the case of 2 slits. We found an approximate formula for all the maxima and all the minima. We're not going to do that for multiple slits, although we could. Continuing with this example of 4 slits, is 90 degrees the only phase difference that produces a perfect destructive interference? Or is there another or several more phase differences that also get those phasors to add up to 0? You could probably figure this out. Take a moment, see if you can draw a picture. See if you can add the phasors up in a way such that they form a closed polygon, just like they did previously, so that the sum of all the phasors is equal to the 0 phasor. Okay, spoiler alert, I'm about to show you the next possible phase shift that produces perfect destructive interference. Oh, I guess I'm not. First, let's show you an angle phase difference between adjacent waves that does not produce perfect destructive interference. So I just arbitrarily chose the angle 150. So we're imagining a particular, I'm realizing that there's really 2 angles here. There's the angle that we're drawing in the picture. That's really the phase difference. And I'm sometimes calling that angle, but then there's the actual angle to the screen, the angle between the forward direction and the screen. Those are 2 different angles. So I will try not to call this an angle. I'll try to call this a phase difference. So if you're looking at the screen at a particular angle out to a field point P, such that the path length difference between adjacent slits is equal to this particular, or corresponds to this particular phase difference, what happens when you look at the total field? So now we go in the direction of phasor 2, rotate by 150 degrees and see what happens. That's 3 slits. We've got 1 slit left. So go in the direction of phasor 3, rotate by another 150 degrees counterclockwise. And how do we add all these up? We go from the tail of the first phasor to the tip of the last phasor. And there it is. Evidently, the total field amplitude is not 0. So there is light intensity arriving at the field point P in that particular direction. So you would not get You would not call this perfect destructive interference. It's also not max constructive because, of course, we could add all these phasors in parallel and get a much longer total phasor. That would be the max constructive. So this is somewhere in the middle. There would be some light arriving at the screen here, but it wouldn't be as bright as the maxima, and it's certainly not dark. Somewhere in the middle. Okay, what about this? What if the second phasor is phase shifted by pi radians, also known as 180 degrees, with respect to the first phasor? Those two alone evidently produce max destructive interference. So they're totally out of phase, we would say. If it was just, if the point P was only being illuminated by these first two slits, you wouldn't see any light because they interfere destructively. However, phasor 3 represents the wave arriving from slit 3. It would also be phase shifted by 180. So let's go back to phasor 2, this one in the middle. Rotate counterclockwise by, and I'm realizing I probably should have put the label on the other side. Did I do this right? So this second phasor, rotate it counterclockwise by 180, and it would point that way. And yeah, so it does point to the right, but I'm drawing it tip to tail with phasor 2. When you add these three up, you do not get 0. In fact, the total phasor here between the first three would just be equal to the third phasor because the first two cancel. So if it was just up to the top 3 slits, you would have non-zero intensity at this field point P. However, don't forget about the fourth slit, also phase shifted by 180 degrees from the previous one. So when you add them all up, you still get a total phasor of 0. So here's a different angle theta, a different direction to the screen, corresponding to a different path length difference between adjacent slits, resulting in a phase shift of 180 degrees, not 90. But this phase shift also, I should say this phase shift between adjacent slits also results in a total field amplitude of 0. So there's no light intensity at this particular angle to the screen. Again, when I say this angle to the screen, I'm not talking about the angle 180. That's the phase angle or phase difference between adjacent slits. It's not an actual physical angle in space. The physical angle in space is what you plug into d sine theta. That's your path length difference. Then you take your path length difference, compare it to the wavelength, multiply by 2 pi, and you've got your phase angle difference, phase difference. Let's do another one. What about 270? I'm going to rotate by 270 degrees counterclockwise to get the second phasor. What's this white square here? Let me see if I can fix that. I took the easy way out and just made the whole thing white. Okay, so what if the path length difference between adjacent slits is such that the phase difference between those two waves is 270 now? So I'm going in the direction of the phasor from slit 1, and I would need to turn counterclockwise by 270 degrees to arrive at the direction of the next phasor. And then I look at the wave arriving from slit 3. Again, the path length difference is such that the third phasor is phase shifted by 270 degrees from the second phasor. So I turn from this direction, counterclockwise, 270. Wait a minute, that's clockwise, isn't it? Did I goof that up? Yeah, that was incorrect. This dotted line should better represent how you'd have to turn from the direction of phasor 2 to get to the direction of phasor 3. And then we do this one more time. Go in the direction of phasor 3, rotate counterclockwise by 270. I did it right that time. And we get to the direction of phasor 4. So just like the case of a phase difference of 90 degrees, we end up with this square for which, of course, the total phasor is 0. What's the total phasor? It's the phasor that goes from the tail of phasor 1 to the tip of phasor 4. Of course, those 2 points are the same, so that's the 0 phasor. The picture looks a lot like it did for the 90-degree case, but it's really not the same picture. If you go back and compare the arrows add up in a different way. It's still a square though. So we've now found 3 phase differences between adjacent slits for which the total field amplitude is 0. 3 different phase differences that produce perfect destructive interference. That would correspond to 3 different directions in space away from the forward direction. So let's look at the pattern here. In each case, the phase difference is an integer multiple of 90 degrees. The one we just looked at, 270, is 3 times 90. Before that, 180 was 2 times 90. Is this a general pattern? Can we now predict a 4th phase difference between adjacent slits, which also produces perfect destructive interference? And for each of these phase differences, you plug that number in, plug this angle in here. And I guess to be consistent, instead of 2 pi here, I probably should have written 360 degrees. Of course, you could express these angles in radians. This would be a pi over 2 radians, pi radians, and 3 pi over 2 radians. Each of those phase differences between adjacent slits corresponds to a particular direction in space. That's the direction between the forward direction to the screen and a ray to a point P anywhere on the screen. So let's try this next one. Let's see if 4 times 90 degrees also produces maximum destructive interference. And let me point out, we're talking about 4 slits, and we've already found 3 directions or phase differences that produce total destructive interference. Well, 4 times 90 is 360. If you rotate counterclockwise by 360 degrees to find the direction of the next phasor, well, they're still pointing in the same direction. So when you add them all up, you do not get perfect destructive interference. You actually get maximum constructive interference. So 4 times 90 is no good. Evidently, only these first 3 worked. We had to stop at the 3rd one. So let me point out that result. 4 slits, 3 directions, which gave perfect destructive interference. Let's see if the same sort of pattern holds for 5 slits. So imagine that our partition here, instead of having a double slit cut into it or 4, we've got 5 slits, but each slit is the same separation from the previous one. So that lowercase d would be the same. And maybe I should point out that if I go back here, for 4 slits, you'll notice that 90 degrees, which was our basic unit of phase difference, that's 1/4 of 360, right? 4 slits, 1/4 of 360 to get the basic unit of the phase difference. So maybe that works for 5 slits. Let's take 360 degrees divided by 5, which is 72. Let's try phase shifting each phasor by 72 from the previous one. So here's the phasor representing the arriving wave from slit 1. And let's suppose that the arriving wave from slit 2 is out of phase from the wave from slit 1 by 72 degrees. And then the same thing for wave 3, etc. And yes, you can see why the total waves produce, or all 5 waves together produce total destructive interference. You wouldn't get that from 2 individually. If you covered up the bottom 3 slits and just looked at the light arriving from the first 2 slits, so ignored these top 3 phasors, the total phasor from the first 2 would be this phasor, which does not have an amplitude of 0. So you would see some light intensity at that point on the screen if you covered the bottom 3 slits. But when you uncover all 5 slits, it's kind of counterintuitive, right? You would think that that when all 5 slits are uncovered, you'd have more bright light at that point on the screen than you would with just 2. But that's not how waves work. That's not how interference works. So 5 waves actually interfere destructively, and you get less light than you would with only 2. And maybe this is reminding you of polarizing filters, and how if you insert a third slit between the first 2, you can get light where there was none before. Like if you have 2 crossed filters and you put a third one in. But this is really a different phenomenon. You don't want to muddle those 2 in your mind. They're both kind of surprising features of light, but polarization isn't really an interference phenomenon. That really comes down to the vectorial nature of the electric field. This is an actual interference phenomenon. What happens if we try double 72 degrees? Remember, for 4 slits, we found that 90 degrees produced total destructive interference, and then 90 times 2, which is 180, 90 times 3, which is 270. Does the same thing work for 5 slits? Our basic unit was 72 degrees. Let's try double that. Let's see what happens when the phase difference between adjacent slits is 144 degrees. And I'm doing this one step at a time so you can visualize rotating counterclockwise by 144. And I really do encourage you to take a protractor and a ruler and do this on paper. It's very satisfying, strangely enough. So I've drawn 4 phasors. We're almost done. Aha, do you see what's happening? If I go in this direction now from phasor 4, rotate counterclockwise by 144 degrees, now you see that the sum of these 5 phasors is 0. I've got a closed, it's not a closed polygon really, is it? I don't even know what you would call this. But if I try to draw the phasor from the tail of phasor 1 to the tip of phasor 5 now, I get the 0 phasor. So the total phasor here is the 0 phasor. Of course, that means its amplitude is 0. So even though 5 different waves are arriving at this particular point on the screen, the total electric field amplitude is 0. So you're not going to see any light intensity there because intensity is proportional to the square of the total amplitude. The total amplitude is 0. So we've already found two directions in space which correspond to 2 different phase differences for which you get perfect destructive interference. Remember, this angle 144, that's the angle in the diagram, the Phasor diagram. It's not the angle from the forward direction at which you get perfect destructive interference. Those are 2 different angles. They can't be the same anyway because we're assuming that these angles in space are all small angles, right? The small angle approximation. Although we're going to see that for diffraction gratings, which have many, many slits and a very small slit separation, lowercase d, these angles are actually large enough, the angles of constructive interference are large enough that you cannot use the small angle approximation. Okay, that's a separate point. Okay, so does this pattern hold in general? If you have n slits, whether it's 4, 5, 12, 1,000, I'm going to use this notation, delta phi sub 1. You just take 360 degrees or 2 pi radians and you divide it by the number of slits you're talking about. That's what I was calling your basic unit of phase difference in a previous slide. And it seems that you can find a whole set of phase differences that result in perfect destructive interference or max destructive interference just by taking integer multiples of that first phase difference, delta phi 1. However, you have to stop short of multiplying by n. So for the case of, let me go back here, for the case of this pentagon, no, we didn't go all the way. For the case of the square, right, the base phase difference was 90. We found that the first 3 multiples of 90 worked. And this is 4 slits we're talking about, but the 4th multiple actually produced constructive interference. So you have to stop short of n, where n is the number of slits. Now, I didn't go all the way with the 5 slits. I showed the first 2, 72, 144. If you checked them all, and if you have nothing better to do, you could do that with the protractor and a ruler, you would find that the first 4 multiples worked. So you could go all the way up to 4 times 72 degrees. That phase difference would also produce total destructive interference, but 5 times 72 would not work. That would give you constructive interference. So the general rule is you stop short of n. You go 1, 2, 3, all the way up to n minus 1 times that basic unit of phase difference. That's the set of phase differences that will give you total destructive interference or max destructive interference. So we can summarize that nicely with this formula here, that the mth phase difference between adjacent slits, which gives you max destructive interference, is just m times 2 pi over n. Just take 360, divide it by the number of slits, and then take multiples of that. And the multiples go all the way up to n minus 1. Easy rule. Why does this work? Well, this is a property of polygons that you may have learned in high school at some point. The sum of the exterior angles of a polygon has to be 360. So here, this particular graphic says a regular polygon. It doesn't even have to be regular. Any polygon, if you sum up the exterior angles, you're going to get 360. And what is an exterior angle? It's exactly what we've been describing. If you're going in the direction of one of the sides, the exterior angle is the direction or the amount by which you have to turn to get to the direction of the next side. And when you add all those up, you get 360. It makes sense, right? Imagine you're walking along the perimeter of this polygon here, and just think of the direction that you're facing. That direction is changing as you walk around the polygon. You have to turn. What's the total amount by which you turn when you return to your starting point? Of course, it's 360. So that's evident geometrically, but we can also show it with the formula, because what do you get when you add up all of these delta phi sub m's? Well, there are n of them, right? If you have 5 slits, you have to add that quantity up 5 times. So n times the turn from one phasor to the next would be n times this expression. And then you see that capital N upstairs cancels capital N downstairs. And we find that the total turn that you go through is some integer multiple of 2 pi. Okay, so that's kind of surprising. This formula is telling you that if you do walk the perimeter of this geometric figure, the total angle through which you turn, which is number of slits times the phase difference between each successive pair, or each pair of successive phasors, is not just 360, it could be any multiple of 360. Now in this picture, it sure looks like it's just 360, right? You're only going to turn around once. The direction that you're facing only goes around by 360 one time. But I guess other values of m are possible. Go back to, for instance, this one. This makes it pretty clear that as you walk around this 5-sided star here, you would actually turn multiple times. All right, so now we're getting in, or this is a bit of a distraction with properties of, I don't even know if you'd call this a polygon, but it's worth noting that the total angle through which you turn is some multiple of 360. Okay, so now we can answer the question with the formula. How come that last multiple doesn't give you destructive interference? We've already seen an example of it with 4 slits, but what happens if you plug in the number of slits as your index m here? Well, in that case, the phase difference between adjacent slits would be n times your basic unit of 2 pi over n, but then the n's cancel and you're left with 2 pi. But of course, that doesn't give you destructive interference. If each phasor is turned by 360 degrees from the previous phasor, then you get a picture like this. They're all in phase, so to speak. That's the condition for getting the max possible total amplitude. So that's not going to work. Here's an example that I produced in Python. What can we observe about the interference pattern coming from 6 slits? Well, we've certainly got our bright fringes, 1, 2, 3, also called the interference maxima. Now, previously, when we looked at the interference pattern from 2 slits, we found that the minima were halfway between the maxima. So if this is a minimum, if this is a maximum and this is a maximum, then an interference minimum was right here in the middle. But now we see something a little more complicated. There are actually several minima. See the vertical axis here? This is 0 intensity. I actually count 1, 2, 3, 4, 5 minima in between the maxima. So it's a more complicated interference pattern than the one for 2 slits. Look at the relationship here. 6 slits, 5 minima. That's exactly what we just showed, right? For n slits, you can find 1, 2, 3, dot, 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 up to n minus 1 phase differences between adjacent slits for which you get maximum destructive interference. We've already looked at the program for determining those various directions, right? The delta R is the d sine theta. D sine theta over lambda times 2 pi is equal to your phase difference delta phi. Geometrically, we've already figured out with phasors how to find the delta phis. So use geometry to find the set of delta phis for which you get destructive interference, max destructive, and then go back to the previous formula to actually find the angle theta, the direction to the screen that produces or that corresponds to that phase difference between adjacent slits. Yeah, you know, I don't even know why I put primary maximum because I think we just call them maxima. Okay, fine. Primary maximum because we've got these additional maxima, these little baby miniature maxima down here, which we will call secondary maxima. Okay, so the primary maxima, those are what we call the bright fringes. But evidently there are some additional, much weaker interference maxima in between the primary maxima. And here's the pattern. If there are 1, 2, 3, 4, 5 minima, then you can see that how there has to be 4 maxima, secondary maxima, in between those minima. That's just, I guess it's self-evident just by looking at the picture. So there's your rule. If there are n slits, then in between the primary maxima, those are the bright fringes, you will find n minus 1 minima, that's positions of max destructive interference. And if there are n minus 1 minima, then of course there have to be n minus 2 secondary maxima between bright fringes. And if you want to see why, just look at the picture. I mean, there's no other way for it to work, right? However many minima there are, just subtract 1, and that's the number of secondary maxima. So that's probably worth memorizing. N slits means n minus 2 secondary maxima. Now, is this really how it works? Should you be convinced at this point? Well, I produced this plot in Python by modeling these n waves using phasors. So this, to me, this is already pretty convincing. But you could also go to some actual images of multiple slit interference patterns. So I pulled this off the web. And before we look at the relevant pictures on the right here, let's look at some features of the plot of intensity versus position. You can see that for 4 slits, the max intensity is considerably greater than it is for 2 slits or 3 slits. And we'll talk about that in just a moment. But let's confirm, let's see, 4 slits. If n is 4, then n minus 2 is 2. And sure enough, yes, there are 1, 2 of these secondary maxima in between the primary maxima. For 3 slits, 3 minus 2 is 1. That's why it's no surprise that we only see 1 secondary maximum. And for the case of the double slit, which we looked at first in a previous presentation, 2 minus 2 is 0. You would not expect any secondary maxima, and you do not see that. There are no secondary maxima between the bright fringes for the double slit. And here it is right here. This, I don't think these are actual photographs, but it shows you what the interference pattern might look like on the screen. For 3 slits, you can see that there's 1 secondary maximum between each pair of bright fringes. And then there are 2 for 4 slits. Can we see an actual picture? Yeah, this was in the previous presentation. So it's pretty clear that this actually works. How cool is that you can explain it with phasors? Now, what's going on down here? First of all, you can barely read this, but 5 slits, that means n is 5, n minus 2 would be 3. We would expect 3 secondary maxima in between each pair of bright fringes. I don't really see that here. The reason is the heights of those secondary maxima are so low that your eye just doesn't even perceive the intensity. Do you see how the heights of the maxima are getting squashed down? Can I go back to, yeah, these are really low. And the sensitivity of the human eye to intensity is probably not linear anyway. Like, let's say that the height of this peak here is 10 times the height of this peak. That doesn't mean that your eye will perceive it as being 10 times as bright. It's possible that 1/10 the brightness is really perceived as like 1,000th. Excuse me, let me back up. It's possible that 1/10 the intensity is perceived as 1,000th the brightness, in which case you might not expect to see any of these secondary maxima. So the height of the secondary maxima gets squashed down as you introduce more slits. And that's why down here for 7 slits, when we would expect to see 5, 7 minus 2 is 5 secondary maxima, we actually don't see any. They're so faint that the eye doesn't detect them. Now, an instrument might, like a particular or a special type of camera might be able to detect the intensity of all those secondary maxima. What do you notice, though, about the spacing between the primary maxima as you introduce more slits? That doesn't change. The separation between the bright fringes, that's the primary maxima on the screen for 7 slits, is the same as it was for 2 slits, as long as you're talking about the same slit separation, that's lowercase d. What does change is the sharpness of the maxima. Here's another nice graphic. Again, when I look down here, I don't really count 3 secondary maxima between primary maxima. 5 minus 2 is 3. You would expect to see 1, 2, 3. And at least they're showing you that with the graph. But do you see how the highest secondary maxima just kind of gets blurred in with the primary maxima? So it gets difficult to see this. Now, in an actual lab, like Pasco, for instance, sells these plastic wheels with a number of different slit setups. And you can see this very clearly with a laser beam. The next best thing, if you don't have access to an actual lab setup for investigating multiple slit interference with lasers, would be to simulate it. So that's what I've done here in Python. And this is not just a graph of intensity versus position on the screen. I'm actually going to produce here a 2-dimensional picture of what the interference pattern would look like. And doing it this way actually has some advantages over the real thing with lasers, because you have total control over the waves. And what you find is that the pattern produced is exactly what you would expect. It also matches with real interference patterns produced with lasers and slits. So let me just briefly walk you through what I did here. I'm going to go into more detail about this script here in another presentation. But first I had to import a couple libraries. This one is for plotting. And of course, NumPy is so I can use functions like sine and cosine and the number pi. And then I've defined a number of constants here. So you see the familiar lowercase a. We have not yet talked about the diffraction pattern from a single slit, but the width of each slit is important in the way the interference pattern looks. Right now, we've just been concerned with the slit separation, which is lowercase d here. So in this script, lowercase a is the width of each slit, d is the separation between the slits, h is actually I'm using as the height of the laser beam. And I looked that up. It's about 0.5 millimeter for the lasers that you would buy from Pasco. Because right now we've been talking about the separation between the slits. We're assuming that all of the slits are illuminated by the same beam. But if you think about each individual slit and the light coming from the slit, you would need to know what the height of that slit is. And that's really just the height, or the height of the slit would be effectively the diameter of the beam. Even if the slit was taller than the beam itself, you don't have any light waves coming from the part of the slit that's not illuminated by the beam. So for me, the effect of height of each slit would be the diameter of the beam. Now this lowercase b is the dimension of the square screen that I'm going to create. We'd like to know what the interference pattern looks like on the screen itself. Now I can't just make a screen that's like 1 meter by 1 meter. That would be an insane amount of calculation for my laptop to do in order to find that interference pattern. So we're just going to zoom in on a very small patch of the screen, and all of these numbers are SI. So I'm going with this a screen patch that's 3 centimeters, 3/100ths of a meter on a side. So we're definitely just zooming in on a small part of the screen. And that's all you really see anyway when you shine a laser through multiple slits. You just see a rather localized interference pattern. 50 centimeters away from the forward direction, you're not going to see anything. And then I have to decide how many computations to ask my computer to do. So I'm taking the width of each slit and approximating it with 20 points across. So for me, points A is basically the number of pixels as you go across the slit. Remember in Huygens' principle, when a wavefront encounters an aperture, an opening, a gap, you consider each point on the wavefront as a new source of waves. And again, I'll go into more detail about this later, but I'm basically choosing the number of pixels to use to represent the slit. If I choose a number that's too large, like 2000, it's going to take the computer forever to produce a plot. And then I did something similar for the number of pixels along the height of the slit, and more importantly, the number of pixels on my screen. So I've already decided that the patch of screen I'm going to look at is 3 centimeters by 3 centimeters. And I have to choose how many pixels to put into that little square patch for approximating the intensity on the screen. The greater number of pixels I choose, the higher the resolution of my image, which is good, but that would take the computer longer. So I've gone with the modest 50 pixels by 50 pixels for representing this interference pattern. All right, then more familiar stuff here. We have to choose the wavelength. I'm going to go with something in the middle of the spectrum, the visible spectrum, 500 nanometers. I'm using the symbol pi for the actual number pi. So this is NP dot, that means numpy. That's my abbreviation here for the numpy library. And so this is just telling Python, hey, use this Greek letter pi to actually represent the number 3.14159, etc. Okay, and then K, my wave number, that's 2 pi over lambda. We've seen that. And then I chose a distance of 1 meter between the slits and the screen. All of these things can be changed very easily in the script, and the later commands refer to those values. So you can update them simply in the script and then hit play, and everything will update automatically. Okay, now I'm defining a function that calculates the distance, which I'm calling r, between a point on the screen. So that point P, we've been looking at it kind of one-dimensionally, really. But now I'm imagining any point on this two-dimensional screen in front of these slits, and I'm giving it coordinates x and y, and I'm looking at the distance between that point on the screen and a point within one of the slits. And I'm calling the coordinates of that point within the slits xp and yp. I don't remember why I went with that choice, but xy are the coordinates of a point on the screen. XP and YP are the coordinates of a point within one of the slits. And I need to know the distance between those 2 points. And for that, I just implement the distance formula. So this function accepts 2 points. You plug in the field point P, you plug in a point within the slits, and what pops out is the distance between those 2 points. And then, knowing that distance, I need to find the phase of a wave arriving at the field point from the source point. I got that backwards here. And let me highlight that again. We need the phase of a wave arriving here on the screen from this point, which is on the on one of the slits. Okay, so this is really the phase of the wave, and I'm suppressing the dependence on time. If you go back to our progressive wave functions, we used sine or cosine of kx minus omega t. Well, I'm freezing time at a particular moment. We don't care about the time dependence. So throw that out. And we really just need to know kx, except now it's kr, because we're not looking at waves traveling one-dimensionally along a single axis. We're looking at waves radiating outwards from a point on one of these slits. So it's really kr now. Okay, and I'll be using those functions later. So this function r is really needed just for this function, and this function phi, which gives the phase, will be used later down here. Okay, now here, you're not going to need to mess with this. We'll probably use this for lab, but I had to create a grid of points on the screen. It's a 3 centimeter by 3 centimeter square grid of points. And again, you could change the dimensions. It doesn't have to be 3 centimeters. That's what this is all about. And then down here, I have to create, what am I doing here? I have to create the slits themselves. So this is all about creating a separate grid of points for the slits. You can see, remember, lowercase a was the width of each slit. So here I'm creating the pixels that go across the width of one slit. Actually, that's accomplished not just with this syntax here, but that syntax in conjunction with this. So we don't need to concern ourselves with the details here, but each of these lines you see is creating a separate slit. This top line corresponds to the central slit, the one, you know, we go in the forward direction away from this slit. And then what I've done here is put 3 slits on either side of that central slit. Here's the 3 on the other side. So I really have a total of 7 slits. If you were to tinker with this script and you wanted to add or subtract slits, you would have to add or subtract rows from this block of code here. Okay, so now all of this together accomplishes 2 things. It gives me a grid of points on the screen that's within that 3 centimeter by 3 centimeter patch at which I want to evaluate the intensity. And it also gives me a grid of points within the slits themselves. That's the sources of the waves. And then I need a function for calculating intensity. This is where I implement phasors. So what I'm doing here, you see a cosine function and a sine function. Think back to the phasor diagrams and just consider one phasor. Look at the horizontal and vertical projections of that phasor. The cosine would give me the horizontal projection of each phasor. The sine would give me the vertical. What I'm really doing in this line right here is calculating the horizontal projection of the phasors from each slit. Actually, it's even more than that, and I will talk about this more. I'm really looking at the phasors from the waves coming from each point within each slit. Up to this point, we've totally ignored in these presentations the finite width of each slit. But it's not like there's a single ray coming from each slit. Each slit has a finite width. So you could even imagine a bunch of rays from within each slit. And so I'm looking at phasors from all these points within each slit for all slits. So it's a little more complicated than what we've been looking at elsewhere in this video. But to summarize, just think of it this way. I'm taking the sum of all the horizontal projections of the phasors from each slit, and then I'm taking the sum of all of the vertical projections of each phasor from each slit. Now, when you sum that up, just think about the diagram with all those red projections. When you add up all the red projections, you get the purple projection, which is the projection from the total phasor. So what I've really done here is find the horizontal projection of the total phasor, and then the vertical projection of the total phasor, and then I square those and add them up to get the square of the total phasor magnitude. But remember, what's the meaning of the length or magnitude of the total phasor? That's the amplitude of the total field. That's what we're interested in. Once you know the amplitude of the total electric field from all the slits, at a particular point on the screen, you square that amplitude to get the intensity. And that's really what this is. This is the square of the amplitude of the total field, because I didn't take the square root, right? So it's already the square of the total amplitude. Great. And then here, all I'm doing is telling the computer, okay, create an empty array associated with all those points on the screen, that 3 centimeter by 3 centimeter little square, and then calculate the intensities at every one of those points. So I'm using a for loop, actually a nested for loop, and that's going to involve a lot of computation on the part of the computer, because think about what's happening. And I will explain this in more detail with some slides in another presentation. But for each point on the screen, I made that 3 centimeter by 3 centimeter square patch and then filled it with a bunch of pixels. And for each pixel, I'm saying, okay, hey, at that point, calculate the wave from slit 1, calculate the wave from slit 2, calculate the wave from slit 3, and then add up all those waves. And it's really even more complicated than that, because I'm actually looking at all the waves from each individual slit. So I may have told the computer to actually calculate all the waves, 100 each from each slit. So if you've got 7 slits and 100 waves from each slit, it's really 700 waves that you're adding up. So there's quite a bit of calculation that goes into just finding the intensity at one point on the screen. And I'm doing that for all points, all pixels within the screen. So you can see how changing these numbers will drastically affect the total computation time for this script, because if I increase the number of points within each slit, then that's more calculations. If I increase the number of pixels on the screen, then that's more calculation. Increasing either of those numbers will make a big difference in the total computation time. Okay, so let's see how this actually works. And by the way, if we look down here at this command, I'm telling the computer to assign a color to each point on the screen that's determined by the value of the intensity there. And this command here about log norm, that's to better approximate the way the eye perceives intensity. I mentioned a few minutes back that a wave that's 10 times as intense doesn't necessarily look 10 times as bright to the human eye. So maybe it's more of a logarithmic dependence of perceived brightness on intensity. And I'm doing the same thing here with how the computer color codes the various intensities. It's basically exaggerating the difference in all the intensities to better represent how your eye would perceive the interference pattern on the screen. So I've got 7 slits here, and I've chosen very modest numbers of pixels so that when I hit play, you can actually watch in real time. This square over here is going to turn red, and you'll see how many seconds it takes to compute this interference pattern. Here I go. And it's done already. At least I thought it was. Invalid syntax. Okay, I must have accidentally hit a button and screwed up my script, so let me fix this. Okay, I had misplaced a parenthesis. I'm going to hit play. When I do, focus your attention over here at this square that turns red, and you can see roughly how many, or you can see how much time it takes to do the calculation. Are you bored yet? Okay, that wasn't too bad. There it is. There's our interference pattern. Pretty low resolution. Again, that's because I chose a small number of pixels for the square on the screen. Don't be misled by these numbers down here. These numbers actually tell you, I believe, the number of pixels that I chose. I must have gone with 50 on a side. It has nothing to do with the actual dimensions in space in centimeters or millimeters. No connection. Remember, I chose a square screen patch of 3 centimeters on a side. So this whole distance here, which is being represented by 50 units on the axis, is actually 3 centimeters. And I think I went with 1 meter as the distance between the screen and the slits. So this is what you would expect to see with an actual laser passing through 7 slits. if you're zoomed in on 3 centimeters, a 3 centimeter by 3 centimeter square on the screen. Now, 7 slits would lead us to expect 7 minus 2 or 5 secondary maxima. And I certainly do not see that here. I mean, this is clearly a primary maximum. It's all blurred together. So we need more resolution. So this time I'll go back and change some of the parameters. Like on the screen, I could go with, instead of 50 points, a much larger number, like 500. But I'm not going to make you wait while this processes. So let me just show you the result. And here it is. I forget how many pixels I chose for the screen, but this time when I zoom in, we can easily confirm the behavior predicted by our Phasor method. Here's a primary maximum, an adjacent primary maximum on the screen, and I can easily count 1, 2, 3, 4, 5 secondary maxima in between the bright fringes. Let's try just a couple different examples here. How about decreasing the number of slits? Instead of 7, let's go with just 4. So I'll chop off these 3. And that means I need to also eliminate them from this piece of code. I think I fixed everything. And let's also zoom in a bit, because you recall that 3 centimeters by 3 centimeters with a low resolution, everything was too blurred together. So I think we should still be able to see what's going on in between 2 bright fringes if we zoom in as much as, let's make that screen square 1 centimeter by 1 centimeter. I think we'll still see what's going on. Basically, I'm saying the picture that we look at on the screen needs to, at the bare minimum, include 2 bright fringes and everything in between so that we can count the number of secondary maxima. And this shouldn't take long because I'm using the same number of pixels for the slits and the screen. So let's see what happens. 4 slits. Okay, it's thinking. Oop, done already. Cool. 4 slits. 4 minus 2 is 2. It's pretty easy to see that there are 1, 2 secondary maxima in between each pair of adjacent bright fringes. So it's really fun to tinker with these numbers and confirm all of our predictions. Later, we'll look at additional properties that are consequences of the finite width of the slits. In other words, we need to look at the single slit diffraction pattern and look at how that plays into the overall interference pattern from several slits. And I'd like to point out that while it was easy to use phasors to locate or to find the phase differences that produce total destructive interference, that corresponds to these minima here in the diffraction pattern, or I should say the interference pattern. It's not obvious how one would go about finding the phase differences that give the secondary maxima. The primary maxima, that's easy. That's where you've got total constructive interference. That is where those 6 phasors in this case would need to all be pointing in the same direction. So the phase difference between them would need to be 0, 2 pi, 4 pi, etc. That's not the case for the secondary maxima. So when you add up all the phasors for the secondary maxima, they would not all be pointing in the same direction. If they were, that would be a primary maximum. So you can even see it's not like the secondary maxima are exactly in the middle of the minima. It looks like it's a little more complicated. This one is slightly off center. So I do not know how to go about, I'm not even sure how one would go about calculating the phase differences that produce these secondary maxima. Let's go back and look at the phase diagram to appreciate that a little bit more. Here's a Phasor diagram that shows you something in between max constructive and max destructive interference. We know that for max constructive interference, all of these brown phasors would point in the same direction, and the green one would have its greatest length. That would be a primary maximum, but we're talking about a secondary maximum. If you're interested in the minima, which is total destructive interference, then the brown phasors would have to form a closed polygon or something like that, 5-pointed star. So this is somewhere in the middle. Now, if you're looking in the forward direction from the slits, theta equals 0. I'm not talking about phi, delta phi, but theta. As theta sweeps outwards from the forward direction, and you go through these successive angles theta, remember you plug theta into d sine theta, which gives you delta r. Then you plug delta r into, delta r over lambda times 2 pi to find the phase difference between adjacent slits. As you sweep outwards through greater and greater values of theta, you're passing through various phase differences for which you get total destructive interference. So you have to imagine how the green vector or green arrow here changes in length. At some points, it's going to go to 0, and then it'll bounce back up to its maximum length, which would just be the sum of the lengths of the individual phasors. But there will be places in between where there's what you would call a local maximum in E total. So we don't need to locate or calculate those phase differences for secondary maxima just to get a basic idea of where they are on the screen. We know that those secondary maxima are roughly, not exactly, but roughly halfway between the minima, and finding the minima is very easy using the phasor method. The last thing we need to do is provide some kind of explanation for why the interference maxima, that is the primary maxima or bright fringes, become sharper as you add more slits. That will be an important feature that we discuss for diffraction gratings, which is basically a multiple slit setup with a great number of slits. We're talking hundreds or thousands. So let's first approximate the shape of this curve by merely a rectangle. We've already seen that by the time you get to 10, 20, 30 slits, these secondary maxima are so depressed, the graph is so squashed down that nearly all the intensity is contained within the central, or excuse me, not the central, but the primary maxima, the bright fringes. So I'm going to approximate them with a rectangle. And remember that intensity is proportional to the square of the electric field. We know that the maximum constructive interference you get, let's say, well, I guess we'll go with 10 slits since that's what's on the graph. If all 10 of those phasors are in phase, if they all point in the same direction, then the total field amplitude, the total electric field amplitude is 10 times the amplitude from a single slit alone. But intensity is proportional to the square of the total field amplitude, or I should say the total intensity from all the slits is proportional to the square of the total amplitude. So 10 times the field amplitude would actually be 10 squared, or 100 times the intensity. All of that to say that when you look at the intensity pattern for n slits, the peak intensity in the center of the bright fringes is n squared times the intensity from a single slit individually. That's one of the facts we need right now. For n slits, the peak intensity within a bright fringe is n squared times the intensity from one slit alone, which is what I've stated here. So the height of the curve depends on the square of the number of slits. Now, strictly speaking, intensity has units of watts per square meter. When you're looking at the screen is two-dimensional. Intensity tells you how the power is focused per unit area. But we're really interested in how the intensity varies just with one coordinate as we sweep left and right across the screen. So over here on the side, I'm going to use my laser to remind you about the actual intensity pattern on the screen. So forget about this graph for a second. This graph shows you intensity versus one coordinate, as you move left and right on the screen. But now let's think about the actual two-dimensional screen that I'm outlining with the laser pointer here. You could look at how the intensity changes as you sweep vertically and how it changes as you sweep horizontally. We're interested in how the intensity changes as you sweep horizontally. We go from bright fringe to dark fringe to bright fringe. So we're not interested in this dependence. let's assume that we've already integrated the intensity over the vertical axis. So we've already accounted for the distribution of power vertically. And we're only interested in the distribution of power horizontally. So instead of talking, strictly speaking, about intensity, which is watts per square meter, we're really interested in the number of watts per meter. For instance, how many milliwatts of total light power are there per millimeter as you scan left and right across the screen? So let's think of the height of this curve now as telling us that, not the power per square meter, but the power per meter. How much power in watts is incident upon the screen per centimeter per millimeter? SI units would be per meter, of course. Okay, and that will allow us to calculate the total power incident within a bright fringe. We would just take the power per unit distance horizontally and multiply by the width of the fringe. Let me give you some easy numbers to conceptualize this. What if there was 2 milliwatts of power within each millimeter on the screen? Those are easy numbers. 2 milliwatts of power for each millimeter. Well, if the width of one of the bright fringes was 3 millimeters, so a rather spread out bright fringe, 2 milliwatts per millimeter times 3 millimeters would give you 6 milliwatts of power incident on each of those bright fringes. Okay, so if you get that, look at the units there, watts per meter times meters, that comes out as watts. So we can really explain why the bright fringes get sharper with increasing numbers of slits just by expressing it in terms of energy conservation. We know that if each of these slits is putting out the same amount of total power, then as you open up more slits, of course, you've got more power being focused into those bright fringes. And with 8 slits open, you would expect twice as much power in each bright fringe as if you had 4 slits. So let me repeat that since I'm not writing these numbers down. If you had 8 slits opened, then the total power in each bright fringe would be twice what it was if you only had 4 slits. In other words, the light power incident within each bright fringe is proportional to the number of slits. So how can we combine all this? Well, knowing this and this is what allows us to deduce that the width of each fringe must get narrower as we open up more slits. Because if you take the height of the curve representing intensity versus position, we've already established that height, which is the height of the rectangle, depends on the square of n. And if the width were proportional to 1 over n, then height of the rectangle times width of the rectangle would be n squared times 1 over n, which would give us the correct dependence of the power within the slit on, not the power within the fringe, on n. N squared times 1 over n is n. Have I confused you? We know that the power incident within each bright fringe depends on, or it's proportional to, the number of slits. And so the only way for the height of the rectangle times the width of the rectangle to give you that appropriate dependence of n is if the width is proportional to 1 over n. So as you open up more slits, the width of the bright fringe goes down. N is in the denominator. The width goes down, but the intensity, that's the height of this graph, goes up. And since that height is proportional to n squared times 1 over n does correctly give us that the total power within the fringe is proportional to n. Here's an exaggerated example with 50 slits. Again, 50 slits would mean a total field amplitude 50 times as great as the field from each slit individually. but intensity is proportional to the square of the total field amplitude. 50 squared is 2,500. So the intensity of the light within each bright fringe would now be 2,500 times as great as the intensity from a single slit alone. As a consequence, in order to conserve energy or to enforce energy conservation, the width of the slit would have to be considerably smaller. So the more slits you open up, the taller the curve gets of the curve intensity versus position, but the narrower the primary maxima get. And it's kind of interesting to see this other feature. You see how the secondary maxima are all really squashed down, but the ones close to the primary maxima start to rise up. See that? These secondary maxima get taller and these get shorter as we add more slits. Now, what would it look like if you went from 50 slits to 500 slits or 5,000? You can imagine these would become so pronounced, and these secondary maxima would be so squashed down that there would be essentially no light intensity anywhere between the primary maxima. And then you're talking about something like this. I don't see any secondary maxima between these primary maxima, the so-called bright fringes. And what you're looking at here is the interference pattern from a diffraction grating, which might better be called an interference grating, because we are talking about the interference phenomenon between the light from many slits. But you can see that the separation between the primary maxima depends on the wavelength. These three different colors are associated with three different wavelengths. So a diffraction grating is the limit of a multiple slit setup as the number of slits becomes very large, and also the distance between each pair of slits goes down. So lowercase d is very small now, and capital N is very large. Okay, so in addition to this fact, hopefully you've been impressed by the power of the phasor. Pew, 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 pew.
4 phasors locked and ready to fire, sir. Fire phasors.